Hey guys, so in previous sections we looked at different types of functions and we analyzed them looking at their critical points, their relative max and min, intervals in which your function is increasing or decreasing, and also the average rate of change, right? How much is it increasing? How much is it decreasing? And we saw that functions, different types of functions, can be used to model different types of real life applications. And so in this section, we're going to look at something called scatter plots, which is a graph of a set of ordered pairs that is used to display and provide information on the relationship between two variables that we want to compare. So it's a graph for us to collect and display data. So for example, if I want to compare and look to see if there's a relationship between the number of hours that I study versus how I do on a test, my test score, then I would collect that data as ordered pairs, and then I would graph it and see if there's a relationship. Similarly, I could also compare two variables such as my heart rate versus how much time I spend exercising. And so once I collect these pieces of data, we can plot them as graphs, as points on a graph, and create what we call a scatter plot. So the points are scattered everywhere, and we're trying to see if there is a pattern, if there is a relationship, something that we call a correlation. Is there any relationship, any pattern that I can see between the two things that I'm comparing? So when you describe a data set displayed on a scatter plot, the relationship between the variables can be described by three criteria: the direction, the form, and the strength. So direction could be positive or negative. If you observe in your data that y looks like it's increasing as x increases as well, then the direction is positive. You can see that here we have a positive correlation on the first graph. And that's very easy to see. It goes up, right? There's a pattern of increasing, so it's positive. And if it looks like y is decreasing as x increases, then we have a negative direction, and the relationship is a negative correlation. So again, that's very easy to observe. Clearly, it looks like it's going down as x increases. And then if you can't observe a positive or negative correlation, then there might not be any pattern, there might not be any relationship between the two variables that we're comparing, in which case there is no correlation. The form is also very important. Depending on where all your points on your graph lie, it might look like your points model can be modeled by a line. So it could be linear, or it could look like the shape of your graph made by your points might best be modeled by a parabola. It might be a U shape. So the form could be linear or non-linear. And then the last thing is the strength. Is it a weak relationship? Is it a strong relationship? Or is there no correlation at all? Okay, so a strong correlation would be if you can draw a line of best fit where your data points are very closely clustered around your line of best fit. So that would represent a strong correlation. If you draw a line of best fit and your data is everywhere, looks like a line but not clustered, then it might not be a very strong relationship, might not be a strong correlation, and it's a little bit weaker. So on your three graphs, the first one on the left looks like it's a positive, pretty strong correlation. Second graph is a negative, again, strong correlation, because you can see that all of the points are clustered around this line of best fit that I can draw. And then the last one has no correlation. So whenever we have a scatter plot, sometimes there is no single line that passes through all of the data points, because we know that data we collect in real life is not always perfect. So the more data we collect, the better idea we have looking at comparing their relationship. So when there's no single line that passes through all of the data points, we try to find one that best fits the data, and we call this line the line of best fit, or a linear regression. If your data is not modeled by a line, if it's a curve or parabola, then you would find a curve of best fit, or a quadratic regression if it's a parabola, or a cubic regression if it's a cubic function. So let's look at an example. Again, an SAT problem that I took out from one of the SAT practices. In here, you have a graph that compares swimming time versus heart rate. So Michael swam 2,000 yards on each of 18 days, and the scatter plot above shows his swim time and corresponding heart rate after each swim. The line of best fit for the data is also drawn, and we want to determine that for the swim that took 34 minutes, Michael's actual heart rate was about how many beats per minute less than the heart rate that is predicted by the line of best fit. So the points represent the actual data, and you can see that the swim that took him 34 minutes long is right here. That's that data point. And it looks like his heart rate was right here. And if I look at the units, it looks like I'm going up 140 to 150. So 2, 4, 6, 8, 10. It looks like every unit represents 2 beats per minute. Okay, so it's the Y values, the Y scale goes up by 2 for every unit. So it looks like 34 minutes is his actual time, and his heart rate would be 148 beats per minute. Now, all of these are his data, and they don't necessarily form a straight line, right? But we can draw a line of best fit, which is drawn right here, that will help us make a prediction. So how strong the relationship is, how close the points cluster around that line, will determine how accurate my prediction is based on the line of best fit. So according to this line of best fit, which helps us make a prediction, the prediction is that if his swim took 34 minutes, his heart rate should be right here, according to the line of best fit on this line, 34, 150. That's the prediction. But in reality, it's 148 beats per minute. And so there's a difference of 2 beats per minute. Okay? So there's 2 beats per minute less is his actual heart rate compared to the prediction, which is actually pretty close. And so that's the purpose of the line of best fit. It helps us make a prediction so that even though none of his swims took 35 minutes, we can make a prediction and we can say, well, if it takes him 35 minutes to do his swim, his heart rate will probably be at 140 beats per minute. So line of best fit helps us make predictions based on our data that we collected to create our scatter plot. And so the strength of the relationship is what we call a correlation coefficient, and we have a letter used to describe how strong this relationship is between the two variables that we're comparing. And so we call this a correlation coefficient, R, so the letter R we use to measure the strength of the relationship, is a measure that shows how well a data set is modeled by a given equation. So our line of best fit, we can come up with an equation for that. Or our parabola of best fit, we can come up with an equation for that, and using that equation we can make predictions. So R tells us how well the data set can be modeled by the equation of the line or the curve that we draw to best fit that data. It analyzes the relationship between a data set and the line of best fit, which is represented by an equation. So if your correlation coefficient R is closer and closer to 0, then there is no correlation, there's no relationship. Your data is everywhere. Okay? The closer R gets to 1, the more strong positive correlation there is, and the closer R gets to -1, there is a strong negative correlation. So the correlation coefficient R goes between -1 and 1. Okay, the closer it gets to -1 is a strong negative correlation. meaning that the data set shows a line that goes down. The closer it gets to +1, there's a strong positive correlation, meaning that the data looks like can be modeled by a line that increases, that goes up from left to right. And then the closer it gets to 0 on either side, then there's no correlation, meaning the data is everywhere. And so let's look at example 2. Which of the following graphs best show a strong negative association between D and T, which are our X and Y variables, the two variables that we're comparing. So keywords here that we want to note: strong and negative. Negative means I want to show a relationship where as X increases, Y is going to decrease. It's going to go down from left to right. And so I can immediately cross out option C, which shows a pretty strong positive correlation, and option D, which doesn't look like it's going up or down. So A and D are both negative, it looks like, but which one is stronger? If I draw a line of best fit, okay, which line of best fit would make a better prediction? And you can probably guess that it would be D, because the points are more clustered around that line of best fit. And so whatever the equation of this line is will give me a pretty or a better prediction than the line of best fit for option A. And then last example, and you have another scatter plot. So data is collected. Now we're comparing years versus energy consumption. The scatter plot below shows the amount of electric energy that is generated in millions of megawatts by nuclear sources over a 10-year period. And so in a 10-year period, how much energy is generated? That's the two things that we're comparing. And if you look at these points, it doesn't look like it can be modeled by a line, right? It looks like starting at year 0, as it moves toward year 6, it looks like my data is increasing, the energy generation is increasing, but then it looks like it comes back down. So instead of modeling the set of data by a line and finding a line of best fit, it looks like it would be better if I try to find a curve of best fit. And so if you look at the options, it says which best models the data in the scatter plot. All of these options are equations of parabolas in standard form. All of these are quadratic equations, so a good review on quadratics. And the standard form of a quadratic equation, you might recall, is y equals ax squared plus bx plus c, where a tells us whether my parabola opens up or down, remember that, and c, just like the constant for y equals mx plus b, the constant here represents my y-intercept. And so the parabola, we have a parabola that is going to model this data. And if you look at the data, it looks like it's probably best modeled by a parabola that opens down. And so in my equation, if it opens down, a should be negative. So immediately I'm going to cross out 1.67 and positive 1.67. Both of these have positive a values. And then option B and D both have negative a values. That means both of these parabolas are opening down. So both of these are fine as of now. And then I want to look at the y-intercept. That's the slight difference as well. In option B, my y-intercept is at negative 745.73. And then in option D, my y-intercept is at positive 745.73. So if I draw this parabola of best fit, this quadratic regression, it looks like I would intersect the y-axis right here, which 745 seems pretty accurate, but it is positive. So My answer would be D. This is the best equation that can model the set of data using a parabola instead of a line in this case. And then using this equation, if we want to make predictions, we can make predictions and say, well, if we want to figure out how much energy is generated after 12 years, all I have to do is plug 12 in for X and solve for Y, and I would have my prediction. So as you look at the practice problems on Khan Academy, you want to be looking at the strength of the correlation. Is it positive correlation, negative correlation? Is it strong? Is it weak? And then you also want to be looking at equations that can model your scatter plot and what the X and Y represents.